Welcome back for the video for chapter 5.1. In this chapter, we're going to be working with rational expressions and rational functions. Rational meaning a fraction. So a rational number is any number that can be expressed as the ratio of two integers. A and B have to be integers. A rational expression is defined similarly as an expression that can be written as the ratio of two polynomials. So here are some examples. 2x minus 3 and x plus 5 are both expressions. So this is a rational expression. Likewise here, this is a trinomial on top and a binomial on bottom. And then we have a minus b over b minus a. These are all rational expressions. So we want to see if we can reduce a rational expression just like we would any regular fraction with numbers. And so we can reduce a rational expression, p over q, if we can factor p into p times k over q times k. So if we can factor them, then we can reduce them. So let's remind ourselves how we reduce a regular fraction. So if we have 9 over 12, we can then reduce this because 3 times 3 makes 9 and 4 times 3 makes 12. And so we can see that they share a common factor of 3. So 3 over 3 reduces to a 1. And so we've reduced this fraction to 3 over 4. 3 over 4. And so we want to do the same thing. This is going to take a lot of factoring practice. I encourage you to print out the factoring flow chart that is in Canvas that will help you go through the different options for factoring. I'm going to show you that. The factoring flowchart is right here in your Canvas course. So if you click on the factoring flowchart, you can download this. This flowchart helps you make some decisions on how you can factor. And so you're going to ask yourself if there's any common factor that you can factor out first. And then you're going to ask yourself how many terms are there. If there are 2 terms, there are 3 possibilities. It could be a difference of 2 squares. It could be a difference of 2 cubes, or it could be a sum of 2 cubes. If there are 3 terms, then there's a possibility that you could factor into 2 binomials, such as this. And if there are 4 terms, you could possibly factor by grouping. If you search in my YouTube, there are some videos just on factoring that you could use as a resource as well. So let's jump into some examples here. So we are just going to get some practice factoring. So I am going to factor this, and I can factor this into 2 numbers that multiply to make a negative 12, but when you add them, they make a negative 4. And so I could come up with my list of factors that make a negative 12. I have a negative 1 and 12, a negative 2 and 6, a negative 3 and 4, and then I have the flip, right? I have 1 and a negative 12, 2 and a negative 6, and 3 and a negative 4. And when I add them, they need to make a negative 4. And so this one makes 12, so that doesn't work. That one makes a positive 4, that doesn't work. That one makes a 1, that doesn't work. A negative 11, that doesn't work. A negative 4, this one is the combination. And then this one makes a negative 1. So this is my combination. So I'm going to have a plus 2 and a minus 6. Or you could write it as a minus 6 and a plus 2. It doesn't matter the order. Okay, so I've got a plus 2 times a minus 6 over, and then this bottom trinomial factors into a plus 6 times a plus 2. And then we can cancel out the common factors. And so we are left with a minus 6 over a plus 6. And that is the reduced expression. Example 7. This one's a little bit trickier. So a lot of times we're used to having the squared on the left, but it's okay to have it on the right. It's just going to look a little bit different. And then we can factor out a 10 and an A from everything. So if we do that, we have 10A times 25 plus 10x plus x squared. So now we're factoring this. So we have an x and an x makes the x squared. And the two numbers that multiply to make 25 but add to make 10 are here. And then on bottom, I can factor out 2a, and I have 25 minus x squared. And then, so we have 2a, and then this is two terms, so it factors into a difference of squares of x, 5 minus x and 5 plus x. So you can see our 5 plus x cancels, our a's cancels, and 2 goes into 10 5 times. So we're left with 5 times 5 plus x over 5 minus x as our final answer. Okay, example 8. This is a good one for practice. We have a difference of cubes. And we're going to use our factoring flowchart to help us here because the difference of cubes is a little bit trickier to factor. And so this factors into, this is a difference of 2 cubes, so we're going to use the rule that is a cubed minus b cubed, and then that factors into a minus b times a squared plus a b plus b squared. So this factors into x minus 1, oops, that's times x squared, plus x plus 1. Because a is x and b is 1. Oops, that's a 1. And then we have, this is the difference of squares, so that's an x minus 1 and an x plus 1. So the x minus 1's cancel, and we're left with x squared plus x plus 1. It doesn't have to be in parentheses, all over x plus 1. So getting familiar factoring is going to make your life much easier in this chapter. And I realize I skipped over examples 2 through 5, so let's go back and look at those. They're a little more simple. Okay, we have x squareds in common, and then 9 out of 12 can simplify to 3 over 3, and 3 times 4. So those 3's cancel, and we have 3 over 4. Example 3, I'm going to do it with a pen. So my y cancels with one of the y's, and my x cancels with one of the x's, and the 4 cancels with a 4 there. So we have 2x squared over y squared. Example 4, we would like to be able to just say 2 cancels into the 4 and part of the 8 cancels into 10, but we have to actually, they have to be things that multiply. And right now we have 2x plus 8 and 4x plus 10. So because there's a plus there, it won't work. So if we factor out a 2, now we have 2 times x plus 4. So these are being multiplied. So these are factors. And then we can factor out a 2 here, and we have 2x plus 5. So now because we have factors on top and factors on bottom, the factors can cancel. So we have x plus 4 over 2x plus 5. And that cannot, these x's cannot cancel because they're not factors. They're being added to 4 and being added to 5. Okay. Let's look at example 5. So example 5, again, we want to factor something out front if we can. So I can factor out a 3, and I have 4x minus 3y. And then I can factor out a 3x, and then I have x plus y. So it looks like 3 is the only thing that is in common. So we have 4x minus 3y over x times x plus y. The other piece that is significant with rational functions is the denominator. So a rational function is essentially just a rational expression set equal to something, where the numerator is a polynomial and the denominator is a polynomial, just like these here, but they're not equal to anything, so they're just an expression. So when we go back and think about fractions in general, we can't have a 0 in our denominator. It causes a fraction to be undefined. And so when we talk about our domain or what values could go into x, in for x or a variable in a polynomial in the denominator, we have to limit that to only values that will not cause the denominator to equal 0. So let's look at example 1. So if we have the function h of t, where h of t is t minus 2 over t plus 1, let's find these values here. So we have h of 0 means I'm going to put 0 in for t, and I get a negative 2. So that one's good. And then if we put in h of a negative 2, we'll have a negative 2 minus 2 over a negative 2 plus 1 gives us a negative 4 over a negative 1 or positive 4. And that's good too. And then what if we put in a positive 2? We'll have 2 minus 2 over 2 plus 1. So we'll end up with 0 over 3. And that's okay. We can have a 0 in the numerator, so that just simplifies to 0, and that one is good. Let's look at h of a negative 1. So we'll have a negative 1 minus 2 over negative 1 plus 1. So that gives us a negative 3 over 0, and that one is undefined. So that's going to be an issue. We cannot use negative 1. And then they wanted us to say the h of 1. So that's going to be 1 minus 2 over 1 plus 1 is a negative 1 over 2. And that's okay. So our domain for h is going to be defined as all t given, so that bar means given or provided, that t cannot equal a negative 1. Okay. It might also be written as we have negative infinity up to a negative 1 with an open parenthesis because it can't equal 1, and we're going to union that with a negative 1 up to a positive infinity. So any real number except for negative 1. That's why we have the open parentheses. So examples 11 and 12. are going to look at the denominator for us in different situations. So the only thing we have to worry about is the denominator. So x minus 2 can't equal 0. So that means that x cannot equal 0. So we have a negative infinity up to 2, parenthesis, union 2 up to a positive infinity. That's our domain. We're going to learn in Math 151 what that tells you when that's not an allowed value. That's exciting. There's something to focus on. Let's look at this one. So we have x minus 3 cannot equal 0, so that means x cannot equal 3. So our domain for g of x is a negative infinity up to 3, union with 3 to a positive infinity. And then for 12, we have to factor this because t squared minus 25 cannot equal 0. So we could factor, or we could set it equal to 0, right? So t squared equals 25, and we take the square root of both sides. So t cannot equal plus or minus 5. So we have two restrictions. So now we have for our domain a negative infinity up to a negative 5, union a negative 5 to positive 5, union positive 5 to positive infinity. So we just have these bleeps where it can't equal there. That's why there's parentheses, and a bleep where it can't equal 5. So in lesson 5.1, we learned how to simplify rational expressions and reduce them by factoring. And then we also learned about the domain of a rational function. So catch me back for lesson 5.2.